So again, we're going to be going from -1 to 5 here. So we're going to have 6 different rectangles to draw. 6 rectangles. And what do you notice about some of those rectangles? Where are they located in this problem? Some are located under the axis or below the axis. Okay? No, everything over here is above the axis now. Okay? So on this side, I'm going to have a rectangle like this. I'm going to have, well, in this case, because I'm not actually starting there. I don't want to have a rectangle with a base there, another rectangle there, there, and there. There's my 6 rectangular bases. Some of them will move up, some of them will come down, based on where the location is. Now, you need to be able to do all 3. I'm telling you now, guys. I'm telling you right now. You need to be able to do all 3. Maybe not all 3 tomorrow, but you need to know how to do all 3 for these kinds of exams. I'm going to give you one of them. I'm not telling you which one it will be, left, right, or middle. But in case we're wondering, just to do this, the left approximation means you start on the left and you draw a line till you hit the axis, you hit the intercept or the intersection, and then go over and back down. Start on the left of the rectangle, go over, back down. I'm showing just the diagram. I'm going to erase this in a second and then do right. I go down from here, I go down to where it intersects, go over and back up. Here, I go up. Is there any height of this rectangle here? No, so just go over and down. That's 0. This one, let's assume it doesn't get as steep as I drew it. That could be a little bit misleading. This one goes up, left approximation, down. This one goes up, there's your left approximation, and back down. So those would be your 6 rectangles, where this middle rectangle, this one here, is non-existing, simply because of that root right there. Okay, that's 0. So I'm going to have 3 negative areas, 2 positive areas. I might have to subtract them. I might get a negative or a positive, depending on the problem. Now, I'm going to do the right one, then I'm going to do the middle one, and then I'll do the math behind all this for the middle one. So for the right one now. How did I get that root? If you want to, just set it equal to 0, and then solve, move the 4 over, take the square root, you get plus or minus 2. Again, set this equal to 0, the original function. Whenever you want the roots, you want to set the function equal to 0.
No, I know, but do you need to do that in order for you to get like that exact?
I would do that because sometimes you might have negative areas and you have to account for that. The other way you can tell is when you do the math behind it, you'll see that f of x value turns out to be negative. So if you don't want to do that, you don't have to actually. And I'll explain why in a minute, I'm trying to show you guys graphically what it looks like, and then I'll show you numerically or analytically in that sense. So for the right approximation, I'll start on the right. Okay, I can really start on the left as long as I start on the right of my rectangle. That's what matters, really. Again, it's all about starting on the right side of the rectangle. It doesn't have to start on the right, actually. I could start here, but start on the right side of the rectangle. So starting on the right, to be consistent, there's my rectangle, overshot. There's my next rectangle, overshot. I go up. There's my next rectangle, overshot. Now here, when I start on the right side for this rectangle, what happened? Why is it 0? The intersection is right here. So if I want to go down, I only go down to where the intersection is, which is right there, and then I make a line over. So there's no height to this rectangle. But here, when I start on this right side, I go down, and then I go over. That's an undershot, right? And then over here, I go down to here, and I go over. That's overshot. So my guess on this one is that overshot, 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 far undershot, undershot, overshot. So this one might be, somewhat even, but we'll see what it turns out to be. That's the right approximation. I'm considering the negative parts as negative area if they're under the axis. Correct. So I start here, I go down until I find the intersection in the right corner, then I move over and up.
This is my right.
Correct.
Not that rectangle.
You're right, or the rectangle's right. It's the same thing really, because the rectangle the base is here, right? The right side is there. So start at the right, go down and over, as opposed to the left. The left approximation for this one would have looked like this. You would have gone down and then over like that. That would have been a left approximation. Okay? Middle approximation. It's pretty self-explanatory, right? Middle means middle or midpoint, either one, right? So I start at the middle. Here's my point to start. I go up until I hit an intersection. Then I draw my rectangle. This is, I think, the easiest one for people, actually. Seems to have less confusion, middle. Not sure, graphically speaking. Mathematically, maybe it's the same. But graphically, people seem to be easier with this. They go up to the middle, and then they draw a line through the middle, and then just finish off the rectangle. Go up to the middle, draw a line across the middle. There's the middle, finish off the rectangle. Notice all those points I'm putting there, okay? I go down, find the middle, draw a horizontal line, make a rectangle. Go down, middle, horizontal line, rectangle, down, middle, horizontal line, rectangle. Okay, there's all my rectangles there. Now, for this kind of a problem, I want to think about the simple concept that I have over and under for every time, right? With middle, always have that under and then over, depending on where you are in the function. Now we got to go back to mathematically to figure this out. Remember, how did I figure out the width of every rectangle? Up here, right? So what's the width of all these rectangles again going to be? 1. So every rectangle has a width of 1. So when I want to find the area, I know what the area is width times the height, right? Or base times height. So for all of these problems now, I want to remember that the area is always the sum of all the widths and all the heights. Well, the widths are really the delta x's, aren't they? So mathematically speaking, I write delta xi to show the width of all of these. All of these. Okay? The next thing I write down is f of xi. And all this means is that I'm taking the width times the height for all of my rectangles. That's what it means mathematically. Okay, let's write this out as a series now, though. How do we write it as a series? We say, well, let's take a look first. I'm going to do the middle approximation, by the way. I said that, okay? Middle. So I want to know what the delta x is for all these. Well, they're all 1s, aren't they? So isn't this just a constant? Isn't it always going to be 1, delta x? All these rectangles have a width of 1. So what can I do with a constant always? Put it on the outside. So I know that there's going to be a delta x out here. And I'm going to multiply it by all of the heights. I have to do the width of one rectangle times the height. The width of the rectangle times the next height. Times the next height. How many heights am I going to have total? I'm going to have 6 totals. Okay, I have 6 heights because I have 6 rectangles. So I need to figure out what those 6 heights are. And they're all going to be multiplied by 1. So this delta x I factored out. Because I could put it next to all of them, but that's just redundant, isn't it? Okay, it'd be like 1 times this, 1 times this. The delta x really could drop off now because it's a 1 in this case. If it would have been half, it wouldn't have dropped off. How do I find the height of my rectangles, though? How do I find the height of this first rectangle, Kenny?
You plug it into your function.
Plug what in? What's it?
Value of x.
Where's the value of x?
1. We already know it's 1.
Yeah, the value of x is 1 for this one?
I'm sorry, from the where it is from like the x-axis. Since we know it's from -1 to 0.
So what's the height? What location are we looking at? The midpoint. Very good. So the height of this function is designated by this location right here, really, right?
Oh, okay.
Which is the midpoint because I'm using MRAM. If I was using LRAM, I would have used the point on the left here. So this is f of what?
-0.5.
-0.5. So I have to evaluate my original function at -0.5. So this first one is f of -0.5. Christian.
When you say the sum of all the delta x's, what did you think? You said it was like-
It's the sum of the product of these. So if I had a delta x next to all these, because that's what this is saying here, I'm factoring it out. So it's not 6. You're not summing up all of these plus the sum of all these. You're taking the sum of the product. I happen to factor that out front, which means now I've factored out this outside the summation symbol, and now I have the delta x out here, and I'm only summing these. That's why there's going to be a plus sign between all these parts. Okay, but that part has been factored out already. So now I need the other 5 rectangles still.
So what's the height?
What's the next rectangle? How do I find out the height of this rectangle? F of 0.5. Jocelyn, what's the next rectangle? F of what? The next rectangle, Kenny. Karen? Next rectangle, what's its height going to be? Come on, stand.
Height or its midpoint?
So again, the first one was 0.5, -0.5, 0.5. The height of this is 1.5, f of 1.5, f of 2.5, f of 3.5, and then f of 4.5. Notice what's happening. You're doing f of what?
You just said question about the delta x.
Yeah, the original number plus whatever the delta x is. Remember here, this is f of 0.5. The next one is f of 1.5. What am I going up by? I'm going up by the delta x. Notice these increments? They're all going up by 1. So I've got -0.5, 0.5, 1.5,
Go.
2.5, 3.5,
You got 4.5.
4.5. Thank you. We're going all the way up to 5.
We need a longer board, just a little bit longer.
I just gotta write smaller.
I like here.
And Kenny, how'd you know we were missing one?
Because it had 6.
Good. There's 6 rectangles. So the easiest way to remember this, guys, your delta x, yeah, that's a value of 1. And that's great. And I can factor it out because I'm going to multiply the width times all these. But each of these heights are how far apart? 1 unit apart, which is the delta x. So if you're ever forgetting what to do here, as long as you know the first number, you know all the rest. Again, think about LRAM. For this problem, LRAM would have started on the left side. What is the value here, f of what? F of -1. What would the next rectangle have been? F of 0. So if you knew that this was -1, then this is 0, 1, 2, 3, 4. If you had done RRAM, you would have to start with the right side of this rectangle, which would be f of 0, then f of 1, f of 2, f of 3, f of 4, and f of 5. So all of your f of whatever these values are differ by whatever your delta x value is. Are we clear on that again? This delta x value is a 1. It's the unit length. Okay, it could be something else. If this had been 0.5, then this would have been f of -0.5, f of 0, f of +0.5, f of 1, f of 1.5, f of 2, f of 2.5, f of 3, f of 3.5, f of 4, f of 4.5, then you would have stopped. Again, remember your delta x is how many spots you're going to change. But if this were 0.5, it would have meant we had a lot more rectangles, right? That's what all those extra rectangles I was just talking about came in. So what do you need to do now at this point? You need to go ahead and plug in these values into this equation. If you're given something with MRAM and the decimals are this messy, usually it'll be a calculator. I don't think that they're going to give you something like this where the decimals are that messy without a calculator. They might, but it's rare. If they did, what's an easy way to get around it?
Table?
No calculator. What's an easy way to get around it?
Just decrease all of them by the same.
Good idea. Doesn't work though. I understand what you're saying. What if I think of these all as fractions? Isn't it easier to square fractions than decimals?
Yeah.
I mean, this is 1/2, right? When I square it, it becomes 1/4. This here is 3/2. Square that, it becomes 9/4. This is 5/2. Square that, it becomes 25/4. This is 30. Oh, well, sorry, this is 5/2. This is 7/2. 7/2 becomes 49/4. This is 9/2. 9/2 is 81/4. Whenever you need to square something, a little hint, if you don't know the decimal square of it, convert it to a fraction and then square it. It helps you a lot, it really does.
And we can just leave it as a fraction, right?
Say again?
We can just leave it as a fraction.
And you can leave your final answer over 4, because these would, notice guys, if you wrote these all as fractions, watch what I'm going to do here. If I wrote all these as fractions, this one in the front is fine. F of -0.5, I need to square it and subtract 4. So I need to square this number. This is really -1/2. So if I wrote it like this, that's what the first part turns out to be. That's what I'm doing really for f of -1/2. Then I have to do that for the next one. What you're going to notice is that you're always going to get a 4th here. Always going to get a 4th. And then you can write this as 16/4. And you can really combine all these terms, make them easier. This would be and this one's going to be, so that's the 1/2 there. There's going to be 3/2. So you do 3/2 squared minus 4 plus 5/2. What do you notice the halves are going up by? Odd numbers, or they're going up, they're all odd, they're going up by 2. Okay? It's like a series, up by 2 every time. The last one, or not the last one, sorry, this is going to be plus bracket 7/2 squared minus 4 plus bracket 9/2 squared minus 4. Again, what am I doing the entire time? I'm simply taking in these numbers, I'm squaring them, but instead of writing 4.5, I'm squaring 9/2. Again, the reason here is because it's easier to square fractions. These are all going to be over 4 now. Make all these 16/4, combine like terms, combine everything over 4, and then you get one number over 4 in the end. Okay, one number over 4. If this is a calculator problem, we will definitely install the program on your calculator ahead of time. Okay? Not worth wasting your time. I don't think it will be though. I'm just telling you that now.
If you just
So they do that on purpose because they know that students have a calculator program that can do it for you. All you have to do is enter in the lower limit and the upper limit. So in this case, all you need to enter would be -1 and 5. You enter the number of rectangles, you enter the original function, hit enter, it'll do the Riemann sums for you. And you tell it MRAM, LRAM, or RAM. You can choose. Are you doing that now for us?
What?
Is that what you're doing right now? What did you get?
Left 7, middle 17.5, and right 31.
Okay, which is logical actually. It is logical because of the fact that this function is not symmetric. That's the reason why. Here, notice that this one is increasing, whereas this one decreases, and then increase on this side. Okay? That was only Riemann sums. The other stuff is antiderivatives and fundamental theorem. So it's pretty much doing the integral without the limits. Okay, make sure you know your rules. So we know like the integral from 1 to 5 is really the integral from 1 to 3 plus 3 to 5. You can break it up and stuff. And then the fundamental theorem would be integral with the numbers on the top and the bottom, where you're going to plug in those numbers at the end. Will I be here? I'll be here after the faculty meeting if you want to come by then. Before then, you could come by also. I mean, I have a half an hour before the faculty meeting. So I'll figure out which way is easier for you. Yes, I know. Okay? Absolutely. Tomorrow, sure. Who else is doing it? Is it Kimberly or Rebecca? You guys wanted to do it tomorrow or today? So then why don't you all do it tomorrow?
Like what, 45 minutes or an hour?
No, 3 problems. 20, 25 minutes most.
Oh, just 3 like that?
Yeah, and then we're reviewing.
You're already there.
Tomorrow we're doing only these 3 problems: Riemann sums, antiderivatives, and fundamental theorem. One of each problem, and then we're going to review more about integrals. Thank you very much.
Told yourself on the